Welcome to Day 4, Part 1. In Day 3, Part 2, we went through the 0-1 knapsack problem. In this part, we're going to take a look at making change using a certain set of coins. And there are actually two different formulations of this that you might encounter. Well, there may be other formulations as well, but these are the two common ones. Okay, so each of them has the same basic setup. You have some set of coins, and each of the coins has an integer value. The different coins have different denominations from each other. And from this set of coins, in order to make change, you can use as many copies of each coin as you wish. So, as a trivial example, let's suppose that one of your coins is a penny, and you needed to make change for 4 cents. Well, you can do that by using 4 pennies. Now, the first problem or one of the two problems, maybe I should have called these problem A and problem B, I don't know. One form of this problem is to find the minimum number of coins from the set of coins that's available in order to make some value of change that is greater than or equal to 0. And the other kind of problem is to figure out how many different combinations of coins can be used to make some value of change. So here we have a trivial example. Our coin set consists of just a penny and a nickel, and the minimum number of coins, if we want to make change for 2 cents, is 2 coins, okay? The minimum number of coins that we need to make change for 2 cents from this set of available coins is 2 coins. That is, we can use 2 pennies. The minimum number of coins to make 11 cents worth of change is 3. And we do that by using 1 penny and 2 nickels. Now, in the case of 2 cents of change, there is only one way of making this change. The only way we can do that is to use 2 pennies. But for 11 cents, there are many different ways that we can make change. We could use 11 pennies. Okay, so that's the I was going to say brute force. I don't know. I mean, it's just that's the idiot approach of just making a bag of pennies and handing it back. Or we could use a nickel and 6 pennies, or we could use 2 nickels and a penny. Okay, so of these 3 possible combinations, one of those combinations has the smallest number of coins. But you might be asked either for the minimum number of coins to make a certain value of change, or for the number of combinations of coins that you can use to make a certain amount of change. Now, most actual money is structured in a very reasonable way. For example, in the United States, we have pennies, nickels, dimes, and quarters as the most popular coins that people use to make change. There are 50-cent pieces and there are dollar coins, but those are frankly not used very often. Partly because the 50-cent pieces are so big and the dollar pieces are about the same size as a quarter and people get confused. Okay, so 1, 5, 10, and 25 cents are the most common things. Now, there are 2 properties that these coins have, first of all, that are important. First of all, we do have a 1-cent coin, so it will be possible to make change for any amount of pennies, for any value of pennies, for any amount of change greater than 0. The other thing that's a little bit subtle here, that nevertheless is important, is that each successive coin is worth at least twice of the previous coin. Okay, so 5 is worth at least twice of 1, 10 is worth at least twice of 5, 25 is worth at least twice of 10. The importance of this is that we don't need to resort to a dynamic programming algorithm for making change with American coins. We can use what's called a greedy algorithm, which is faster. And now I'm going to tell you everything you need to know about greedy algorithms in 40 words or less. Okay, so basically a greedy algorithm at each step makes what appears to be the best possible choice at the moment. And we simply don't worry about whether we might at some point in the future have made a better choice. We're going to just make the what appears to be the locally best choice, and we're going to keep moving on. The big advantage of a greedy algorithm as opposed to a recursive algorithm or a dynamic programming algorithm is that it's extremely fast. You know, we just make decision, 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 and that's it. And for many situations, we get a solution that's good enough. You know, it's cheap enough, it's close enough to what we want that we can just go ahead and go with that solution. However, it is absolutely not guaranteed to produce some kind of globally optimal solution. It may or may not. Now, fortunately, because of the properties that American coins have, it turns out that if we use a greedy algorithm, we will actually get a global optimum. Now, if you think about this in real life, except for people who have trouble counting, you've probably never considered it a problem if you're using American money to just make change for a certain amount. I mean, it's really obvious what you do. You subtract quarters until you use quarters until the value gets below 25. Then you use dimes until the value gets below 10. Then you use nickels until the value gets below 5, and then you use pennies. I mean, it's really straightforward. Nobody has any trouble with it. And so here is an implementation of that. We're putting in our coins in descending order of value, and in order to get the minimum number of coins to produce some value, we're going to set up a return variable that starts out at 0 because we're going to be adding coins to the number of coins that we're going to return, so we start from 0. And then, for this value that we have, for each coin going in the order from quarters to dimes to nickels to pennies, we're going to compute the number of the current coin that we can use. Well, the number of the current coin that we can use is the total value divided by the current coin with the fraction part chopped off. So we're using floor division here, all right? So let's take a look at this example here where we're calling min coins with 63. Okay, so 63 divided by 25 is going to be 2 and a fraction, and we don't want the fraction part, so the number of quarters that we're going to use is going to be 2. All right, so we're going to add 2 coins to the number of coins that we're going to return. Now we need to subtract from the value the 50 cents that we get from the 2 quarters and go back up to the next coin. So the next time through we're using dimes, and we have 13 cents. Floor division gives us 1, so we add 1 dime and then subtract 10 cents. Now we're left with 7. So we use 1 nickel and add 1 nickel and drop down to... Now I've lost track. Okay, let's see. So, all right, so 63 minus 50 is 13, minus 10 is 3. Oh, my mistake. So we don't use any nickels. Oh, I'm sorry, we don't use any nickels. We use 0 nickels. So we've got 2 quarters, 1 dime, and then we're going to end up with 3 pennies. So we've got the minimum number of coins that we need to make change for 63 cents is 6. And you can see that logic works for smaller values and larger values. Now, let's suppose that we have a collection of coins that does not have this nice property that each coin is worth at least twice as much as its predecessor. Okay, our president announces a new executive order that we're going to have an 18-cent coin for some bizarre reason. Now the greedy mechanism will not work any longer. So here are our new coins. We've got a quarter, we've got this new 18-cent piece, and we've got dimes, nickels, and pennies. When we ask what the minimum number of coins that we need for 54 cents is, using our greedy algorithm, okay, well, 54 is going to give us 2 quarters and leave us with 4 cents. So we can't use any 18-cent or 10-cent or 5-cent pieces for 4 cents. And we end up with 4 pennies, giving us a total number of coins of 6. That is, we've got 2 quarters and 4 pennies. Now, there's a typo on this slide. It says 5. I've corrected that in the posted slides, but not in the video. That is, the greedy algorithm tells us that we need 6 coins to get to 54 cents. But that's a wrong answer, because if we had not immediately subtracted quarters and we had been willing to wait and see what happens later, we would have discovered that the 18-cent piece only requires 3 coins to give us exactly 54 cents. Okay, so using 3 18-cent coins is going to be a smaller number of coins than using 2 quarters. 2 quarters. I think there should be a 6. Anyway, you get the idea here. That because the decline in the coin values is not by at least a factor of 2, our greedy algorithm gets messed up. Okay, so let's take a look at a recursive formulation where there is not any kind of rule about how the different values of money relate to one another. Each coin has a value. We don't know anything about the ratios between the coins or what have you. So if we got some value that's greater than 0 and we want to know the minimum number of coins that are going to be required to compute that value, then basically there are 3 situations. If the value that we're seeking is greater than the value of coin sub n, then the number of coins that we need is going to be 1 plus the number of coins that we need to compute the value v of v minus that coin value cn. Now, v minus cn may still be larger than cn, so we may end up using multiple copies of that coin value cn. On the other hand, if the value that we're looking for is exactly equal to the value of the coin cn, then clearly we just need 1 of that coin to create change, and that's the lowest value we could possibly have. On the other hand, if the value that we're seeking is less than the value of the current coin that we're considering, what we need to do is to ignore that coin and just see how many coins we need of denominations other than that particular coin. Now, in our table that implements the number of coins that we need for each possible value, we're going to store the value v plus 1 as the initial value in each slot, since that represents a number of coins that's got to be higher than the total number of coins that you actually need. In other words, let's suppose that the value you're asking for is 10 cents. You can't possibly need more than 10 coins to create 10 cents, because our one rule that we do have is that our coin values have to be integers. Okay, so we're going to deposit 11 cents into each slot as the initial value, and then we're going to see if we can find some set of coins that's smaller than that to make the appropriate amount of change. All right, so for a memoization, let's start out with this array A, and we'll have possible values for the change that we're going to make, starting from 0 and then going up one integer at a time until we get to the value v that we've been asked to create change for. And we're going to be able to build up the minimum number of coins that we need for each of these values, starting from the value 0. Now, initially, as I said, we're going to set each one of these cells to v plus 1, whatever v is, since it's not possible to require v plus 1 coins. That will give us a starting position, and we will try to reduce that value for each one of the possible values up to and including v. And then we have a fairly simple loop to go through. For each one of the coins, some CI in the collection of coins, assuming that the value of the current coin is less than or equal to the value that we're looking for, then clearly we only need one of that particular coin to make that change. So we'll set A of C sub j equal to 1. Now, let's suppose, just for gags, that just for illustration, that the coin we start with has a value of 4. That means that we're going to put a 1 into the slot A sub 4 to indicate that we only need one 4-cent coin to make change of 4 cents. Now, for j going from the next slot up to v, what we're going to do for the next slot is set that value either to the minimum of what it already is. Okay, possibly we have reduced the number of coins that we need to make change for 5 by looking at some other coins. So we'll make the new value for the sub 5 slot equal to the minimum of whatever the lowest value is that we have previously discovered, or 1 plus, okay, 1 plus the value of A sub 5 minus 4 in our specific example. Okay, so if we only need one coin to make change for 4, then we're going to need the minimum of either what's already here or one coin plus whatever the minimum number of coins is we need to make change for 1 cent. All right, and we just keep crunching our way through that loop. Then, when we have finally gone through all of the coins and all of the values from 0 up to v, so this is going to be a nested loop. It's going to be of order n times whatever v is. The final value, a sub v, is going to be the total number of coins that we need. Otherwise, typically this question is phrased in such a way that you're asked to return -1 if if there is no combination of coins that will yield that particular change. All right, so let's see this in action for a particular example. Let's suppose that the value that we're trying to make change for is 10 cents, and we have these coins with values 2, 3, and 6. Our first thing to do is to initialize all of the cells to v plus 1. So we start out with all of the cells being 11. That's an impossible number of coins to make change. We can't possibly need 11 coins to make change for a value of 10, but that's a ceiling that we'll start from. Then, okay, I've copied that initial array A that is full of 11s to the bottom here on slide 12. And now let's suppose that we are starting to loop through our coins, and our first coin, coin sub 1, is got a value of 2. Well, if the first coin has a value of 2, then clearly a sub 2, the minimum number of coins that we need to make a value of 2, is just one coin. So we fill in a 1 into a sub 2. Then we go through all of these subsequent values, 3, 4, 5 up through 10, and we set each one to the minimum of either what's already there or one coin plus the minimum number of coins that we needed to make change for 2 cents less than our current value. So in other words, for the 3 too many clicks. If we're trying to make change for 3 cents and we're doing that using 2-cent pieces, what we're going to ask for is the minimum of either the value that's already there, which is 11, indicating that so far we have not discovered any way of creating change for 3 cents, or 1 for the 2-cent coin plus the number of coins that we need to make change for 1 cent. Okay, we're at value equals 3, and one possibility is that we can't make change, so we've still got 11 there. The other possibility is that we need 1 2-cent coin plus the value of a sub j minus 1. Well, that's also 11. So the minimum of 11 versus 1 plus 11 is still 11. And that makes sense. We cannot make change for 3 cents using only 2-cent coins. Now, on the other hand, for 4 cents, if our value is 4 cents, then the current value of a sub j is 11, but we can also make change for 4 cents by using 1 coin plus however many coins we needed for 2 cents. We only needed 1 coin for 2 cents, and so for 4 cents we need 1 plus 1, and that gives us our value of 2. As we continue on with this coin having a value of 2, it's going to be obvious that we can't make change for any odd-numbered value just using 2-cent coins. Whereas for even-numbered values, we can make change for 2 cents using 1 coin, 4 using 2 coins, 6 using 3 coins, 8 using 4, and 10 using 5 coins. Okay, so that is our second run through. We initialized everything to 11s at first. Now we've gone through again using our 2-cent coin, and we've been able to reduce the number of coins that we need for the even-numbered values in the array. All right, so I have copied that down here on the bottom of slide 13. Now we're considering our next coin. Okay, I've got a typo here. This should be coin C sub 2. Okay, so our next coin is the coin with the value of 3. That clearly means that to make change for the value 3, we only need 1 coin. So we used to have 11 in the slot for value 3, but now we only need 1 coin for the value 3. And then for all these remaining values, from 4 up to including 10, we apply our formula again. So for 4 cents, we've got the minimum of 2, which is the value we already have, or 1 plus, let's see, 4 minus 3 is 11. So we've got a choice between 2, which is a sub 4's current value, or 12. Well, clearly 2 is better, so we fill in 4 with the 2. Now for 5, we currently have 11, but we can do better than that, so we're going to get the minimum of either 11 or 1 plus Okay, 1 plus 5 minus 3 gets us down to slot 2, and that's only 1. So we only need 1 plus 1 is 2 coins now to create change for 5 cents. All right, which is clear. I mean, we need a 2-cent piece and a 3-cent piece. And we keep turning the handle here until when we get to 10, we need either 5 coins. All right, 5 coins is the value that we got just using 2-cent pieces. So we're going to get the minimum of either 5 or 1 plus a sub, well, let's see, 10 minus 3 is 7. And the value of a sub 7 that we could computed a little bit earlier in this loop is 3. All right, so we have a choice between a sub j, which is 5, or 1 plus 3. And from that we get that we need 4 coins using the coin 2 and or the coin 3. And that's, again, that's fairly clear. We need 2 3-cent pieces plus 2 2-cent pieces to get ourselves to a value of 10. Finally, we're going to go through and consider the final coin, which has a value of 6. All right, so our coin value is 6. That means we start by setting a sub 6 equal to 1 cent. And then we turn the handle and go through these values from 7 up to including 10. And set each one of these to the minimum of whatever value it had before, or 1 plus the number of coins that we needed for 6 cents below whatever value j has. So for 7, we have a choice between 3, that's the value we had before, or a sub 1 plus 1, so we have a choice between 3 and 12. We'll take the 3. Then for 8, we have our choice between 3 and 1 plus a sub 2, so that's 2. All right, so we'll take the 2 there. And when we finally get to the end, where we have our old value, our previous value for the value of 10 was 4 coins, 2 3-cent coins plus 2 2-cent coins. Now we're going to need either 4 coins or 1 coin plus a sub 10 minus 6, that is 1 plus a sub 4. Well, a sub 4 was only 2 coins, all right, and so 4 is worse than 1 plus 2 is 3. So we need 3 coins now to make change for 10 cents using the coins 2, 3, and 6. And it's easy to see what those are. It's going to be 1 6-cent coin and 2 2-cent coins. Okay, so that is our algorithm. It's a nested loop. So the performance of this is going to be the number of coins times the size of the value. So the time performance of this is going to be the order Vn. V is the value, N is the number of coins. So in this case, where the value is 10 and we have these coins 2, 3, and 6, we return that we need 3 coins to make change for 10 cents. It could happen that the final slot in this array contains the value 11 still. And in that case, we'll return -1 to indicate that we cannot make change. What would be an example? Well, we have a trivial example that we already saw. What if we asked for change for 9 cents and the only coin that we had available to us was 2-cent coins? We can't make change for 9 cents out of 2-cent coins. So if that's what we're asked to do, we're going to end up with an 11 in that slot for v equal to 9. We'll discover that that value is not less than 11, and so we'll return -1 in a situation like that to indicate that we cannot make change. All right, so that takes care of the minimum number of coins problem. The other form of this question is, how many combinations of coins do you need in order to produce a certain amount of change? And let me catch up here. Okay, so how many combinations of coins could you use to create some certain amount of change? Well, let's think this through, okay? If the value that we're asked to find is 0, then in this case, there's only one possible way of making 0 in change, and that is the empty set of coins. Okay, we're going to include the empty set of coins as the one way of producing a value of change of 0. Otherwise, if the value is greater than 0, then we can split this up according to whether we do or don't use the final coin. Okay, so I was going to say clearly, which is always a dangerous thing for a professor to say. So I will refrain from saying clearly. If we consider whether we do or don't use that final coin, then the number of combinations of coins that we can use is the number of combinations that definitely do use the final coin, plus the number of combinations that definitely don't use the final coin. Right? I mean, the total number of combinations is some set, and if we simply create two subsets, where one subset is combinations that do include the final coin at least once, and the other subset is combinations that never use the final coin, then the sum of the numbers of values in those two subsets must be equal to the total number of combinations. Okay, now let's break these two sets down further so that we can get to a stopping criterion and some values that we can actually compute. All right, so first we'll consider the number of combinations that have value v and that use coin Cn. Well, the number of combinations that have value v and that use coin Cn has to be 0 if the value that we're trying to produce for change is less than that coin Cn, which may seem a little strange because we're saying that this is the set that do use Cn, and yet if we can't use Cn, the number of combinations that do use Cn is 0. That does make logical sense. Otherwise, let's suppose that the value that we're trying to create is greater than or equal to the value of coin Cn, then the number of combinations is going to be the number of combinations that have the reduced value by one coin Cn. And this we also split into two subsets. All right, so the number of combinations that have the reduced value and that do use Cn, plus the number of combinations that have the reduced value and that do not use Cn. All right, so we're basically just applying this same sum again down here, but this time with a reduced value, where we're subtracting one copy of the coin Cn from the value. All right, so that blue sum there, with this or thrown in here, that's the number of combinations that do use the coin Cn. Now, as far as the number of combinations that do not use the coin Cn, well, we're going to consider the combinations that use Cn-1 as their maximum coin. Okay? If there is no coin Cn-1, that is, if the only coin that exists is the coin Cn, then there are no more other there are no other coins to consider, and so the value that we can, or the number of combinations that we can use here is 0. Otherwise, if we're computing the combinations of value v that do not use Cn, that's going to be the number of combinations that use Cn minus 1 plus the number of combinations that do not use Cn minus 1. So again, this is our original two subsets, but this time considering coin Cn minus 1 as the maximum coin to consider rather than Cn, which is handled up here. Okay, well, now we have stopping criteria. We have a stopping criterion for the situation where the coin Cn has a greater value than the value of change we're trying to produce. We also have a stopping condition for the case where there's only one coin and we've already used it. Okay, so now we can actually use this to write some code, which you will have to do, and we end up with, once again, an array in essentially the same dimensions as the minimum number of coins problem. That is, we're going to have ascending values of v for our columns, and the next coin to consider for our rows, and we're going to fill that in starting from just one coin. Okay, so here are our possible values, 0 through 10. 10 is the maximum that we're going to be considering in this illustration. And the rows are the next coin to consider. So if we just consider the first coin, that's a coin with a value of 2. Now, there is one combination of just that coin that produces a value of 0, and that's the so-called null set. Okay, so there is one way of producing a change of 0 with just a coin with a value of 2 cents, which is the empty set, no coins. There are 0 ways of producing a value of 1, and that's from this condition here, where the value that we're trying to produce is less than the coin, so that's a 0, plus another 0 because there are no other coins. So we get a 0 plus 0 is 0 for that case. Using a coin with a denomination of 2, there's only one combination that will get us to 2 cents, which is one 2-cent piece. There's no way of getting odd values, so those are all zeros. And using just one coin, there's only one way of getting even-numbered values, all right? So if we want to compute the value 4, there's only one way to do that, all right? So let's see, 4 is not less than 2. So what is the number of combinations of value 2 using coin with a value of 2? Well, the number of ways of producing, the number of combinations of coins that produce a value 2, we've already computed, and it's 1. Plus the number of combinations with value 2 not using coin Cn, but that is a 0 because there is no other coin. So we get 1 plus 0 is 1. And that logic follows through for any even amount of change. There is only one combination, if we only have a coin with a value of 2, of producing an even value of change. We can produce change of 2 using 1 2. We can produce a value of 4 using 2 2s, a value of 6 using 3 2s, and so forth. So there's only one combination for each even-numbered value. Now, let's suppose that we add another coin. We add the ability to use the coin with the denomination 3. Well, as we described before, there's only one way of producing a value of 0, and that is with no coins. There is no way of producing a value of 1. Okay, because 1 is less than 3. So this is a 0. And if we add the number of combinations using coin Cn minus 1, that is this value. So we're adding 0 plus 1 to get 1. There's only one way of producing a combination of coins with value 3. And that logic also continues. And here I've highlighted the cells that are used to compute these things. So if I have a value of 3, sorry, too much. All right, so if I have a value of 3, then there are 0 ways of doing that using just the 2 coin. There's one way of producing a value of 0 using the 3 coin, and so the number of combinations that we can use to get 3 is the sum of those two values. Okay, because we start with a value of 3 here, and we subtract 3 and discover that there's one combination that will get us to 0, and so this 1 here is the sum of those two cells. And that just continues. So this 1 here is the sum of these two cells, this one is the sum of these two cells, etc. And I won't belabor marching through this. We're just adding up cells as we go. Now, if we have a coin whose value is 6, if we add consideration of that coin whose value is 6, then for all of these possible values, 0 through 5, we can't use this coin 6. And so the number of combinations that will get us to these values is just the same number of, is just the number of combinations if we don't consider the coin of 6 at all. So these first 6 values here from v equals 0 to v equals 5, those are just copied down. And then we finally, when we get to producing a value of 6, now we have 2 ways of producing a value of 6 just considering coins 2 and 3. And we also have one more way of producing a value of 6 using the coin 6. And let's confirm that that makes sense. All right, so how many ways can we get to 6? Well, we can use 3 2s, we can use 2 3s, or we can use 1 6. Those are the only 3 possible ways that we can get to a value of 6. And the rest of this array is filled in the same way. So, if our target value is 10, if our target value is 10, using these coins 2, 3, and 6, there are only 3 possible combinations of coins that will do that. Namely, we can use 5 2s, we can use 2 3s and 2 2s, we can use 1 6 and 2 2s. Those are the only 3 combinations of coins that will enable us to produce a value of 10. Okay, and so that gets us to the conclusion of these 2 different forms of combinations of coins questions that you might encounter. And you're going to have to implement code to represent these this memoized recursive approach to solving each of these 2 problems. All right, onward ho.